各位同学好，我是天津大学张佩 IEEE Fellow. My course is Mathematical Interpretation of Reinforcement Learning in Multi-Step Stochastic Economic Dispatch. I use this title to frame one practical question. When a power system operator faces uncertain load, wind power, and solar power over multiple time steps, can reinforcement learning behave like an optimization method rather than a black box? My answer is yes, but only if the learning process carries the physics of dispatch, the optimality conditions of the economic model, and a safety mechanism that respects operating limits. The course follows that logic. I begin with the mathematical dispatch model, then examine why conventional RL penalties are not sufficient for hard power system constraints. I then build a physics-guided safe RL framework with a KKT-based PINN actor, expert dispatch experience, twin critics, a CMDP treatment of ramping risk, and a convex safety layer. The final pages use a modified IEEE 14-bus test system to show how the method improves cost, convergence, and operational safety. Real-time optimal dispatch is first a cost minimization problem under physical network constraints. The objective combines two economic terms. The first term is the generation cost of thermal units. For generator G at time t, the active power output is PGT, and the quadratic cost is a G times PGT squared plus BG times PGT plus CG. This is the standard convex approximation of fuel cost. The second term represents reserve adjustment cost. Upward reserve and downward reserve are denoted by delta T plus and delta T minus. They are purchased because renewable generation and demand forecasts are never perfect. If wind output is lower than predicted, upward reserve covers the shortage. If renewable output is higher than predicted, downward adjustment absorbs the surplus. The constraints on the right connect this economic objective to power system physics. Active and reactive power injections are computed from voltage magnitudes, voltage angle differences, and the network admittance terms Gij and Bij. Generator output limits prevent impossible dispatch instructions. Ramp limits prevent a unit from changing too quickly between adjacent time steps. Voltage bounds preserve service quality and stability margins. The apparent power limit, expressed through Pij and Qij, protects transmission lines from overloading. The mathematical issue is therefore not only finding a cheap dispatch, it is finding a cheap dispatch that remains feasible in the AC network and across time. A common RL treatment of dispatch violations is to put penalties into the reward. That works for soft preferences, but it is dangerous for hard operating constraints. If a generator ramp limit or a line flow limit is violated in one actual dispatch interval, the grid cannot wait for the average learning objective to become acceptable later. The table distinguishes two families of constrained RL. Safe optimization formulates a constrained MDP. It maximizes expected return while limiting cumulative violations over a horizon. This is useful when constraints are time-coupled, or when occasional small violations can be interpreted as soft costs. Its weakness is immediate safety. A small cumulative number does not prove that every individual step is feasible. Safe exploration attacks the current action directly. A safety layer projects an unsafe action onto a feasible boundary, so it is better suited to hard constraints that must hold at every time step. The limitation is that a boundary projection can trap exploration near the edge of the feasible region and can interfere with multi-step constraints. The engineering challenge is to combine both ideas, a long horizon learning objective for ramping behavior, and a single-step correction mechanism for strict feasibility. The full framework has three interacting sources of guidance. The first is the KKT-based PINN actor. Instead of letting a generic neural network map states to dispatch actions, the actor is trained with residuals derived from optimality and feasibility conditions. This makes the policy gradient point toward solutions that look like economic dispatch, not just toward high numerical reward. The second source is expert experience. Historical and model-based perfect dispatch samples are stored in a dedicated replay buffer. They do not replace learning from interaction. They provide high-quality reference directions, especially in the early phase when a randomly initialized agent would waste many trials in low-quality regions. The third source is the safety layer. The actor may propose an action a t, but the grid receives a corrected action a safe t. The correction solves a projection problem that minimizes the distance between the proposed action and the feasible action. The diagram also shows reward critics and ramp critics, each with target networks and soft updates. This design separates economic return from ramp constraint risk. The power system environment feeds states and rewards back to the learning process, while the perfect dispatch buffer and experience buffer jointly shape training. The result is an RL policy that learns but does not freely ignore dispatch physics. The CMDP focuses on the one constraint class that can still be violated during training after the single-step safety layer has handled an immediate physical feasibility, future ramp rate behavior. The state includes time t, forecasted load, forecasted wind generation, forecasted photovoltaic generation, and the previous thermal generator output. That last term is essential because ramping is a difference across time. The next dispatch cannot be evaluated without knowing the previous dispatch. The action vector contains active power for every thermal generator, every wind unit, and every photovoltaic unit. The agent is therefore choosing an entire dispatch vector, not a single scalar command. The ramp up and ramp down penalty terms are piecewise. If the increase from PGT-1 to PGT is within the upward ramp allowance, the ramp-up penalty is 0. Otherwise, the excess amount becomes C ramp-up T. The downward case is symmetric. If the drop is within the downward allowance, the penalty is 0. Otherwise, the excess drop becomes C ramp down T. Their sum is C ramp T. The projection distance dt measures how far the actor action is from the safety-corrected action. A large distance means the actor is repeatedly asking the safety layer to do too much work. The reward therefore balances economic benefit, generation and reserve cost, ramp violation cost, and projection distance. The constrained objective maximizes discounted reward while keeping the expected discounted ramp cost, JC, below the tolerance XI. This is how multi-step feasibility enters the learning target. The PINN actor uses 3 neural subnetworks to estimate generator dispatch, voltage, and line flow quantities from the dispatch state. These estimates are passed through a PINN layer where the loss is not limited to ordinary prediction error. The KKT conditions create residuals that express whether the candidate action behaves like an optimum of the constrained dispatch problem. The Lagrangian combines the economic objective with equality and inequality constraints through multipliers lambda and mu. The stationarity residual checks the gradient of the Lagrangian with respect to the decision variables. If that residual is large, the proposed dispatch is not near an optimum. The complementarity residual checks whether inequality multipliers and active constraint functions are consistent. The dual residual uses a non-negative activation on the multiplier. The primal residual measures equality violation and inequality violation. Together, these residuals tell the network what kind of mathematical mistake it is making. The final loss adds dispatch prediction errors and KKT residual errors. The terms for G, V, and L compare predicted and target generator voltage and line flow quantities. The residual terms penalize stationarity, complementarity, dual feasibility, and primal feasibility. This is more informative than fitting labels alone. It teaches the actor the geometry of optimal dispatch, so the policy starts closer to feasible and economical actions before the safety layer intervenes. The critic design uses TD3, or Twin Delayed Deep Deterministic Policy Gradient. TD3 is used because deterministic continuous control policies often overestimate Q values. If a single critic is too optimistic, the actor learns actions that look good numerically but fail in the physical system. The twin critic idea reduces that bias by taking the smaller value of 2 target estimates. There are 2 critic branches. The reward critic estimates the long-term cumulative reward after action A is taken in state S. Its target uses the immediate reward plus the discounted value of the next state and next action. The ramp critic estimates the long-term cumulative ramp constraint cost. Its target uses the immediate ramp cost plus the discounted future ramp value. Keeping these 2 critics separate is important. A low-cost action and a low-ramp risk action are not always the same action, especially when renewable uncertainty changes quickly. The diagram shows reward critics and ramp critics, each with a corresponding target critic. Soft updates move target networks gradually, which stabilizes training. The delayed actor update prevents the actor from chasing noisy critic estimates at every iteration. In dispatch terms, this means the agent does not simply maximize a short-term reward. It learns under two value signals, one for economy and one for intertemporal security. Expert knowledge enters through a dual buffer strategy. The perfect dispatch replay buffer stores solutions computed with actual historical load and renewable generation. These solutions assume that future conditions are fully known and that the operator has full decision authority. In practice, that assumption is hypothetical, but it gives a valuable benchmark, the least cost security constrained dispatch that would have been possible with perfect information. The experience replay buffer stores trajectories generated by the RL agent during online interaction. Those samples reflect the actual learning distribution, including mistakes, corrections, and the effect of the safety layer. The method does not rely entirely on either buffer. It gradually changes the sampling ratio. At the initial phase, only a small proportion, about 5%, comes from perfect dispatch data. This protects exploration because the agent still needs to discover how its own actions behave in the environment. As training progresses, the ratio rises toward 15%. The expert data then accelerates convergence and pulls the policy toward high-quality dispatch regions. The business value is practical. Operators already have historical data, forecast data, and offline optimization tools. The dual buffer design turns those assets into learning guidance without forcing the RL agent to become a passive imitator. The safety layer is the hard safeguard. The proposed action may be outside the feasible domain, but the delivered action is the nearest feasible action under a projection objective. The small diagram on the right captures the idea. An unsafe action is moved toward the feasible region, and the safe action is the corrected dispatch point. The objective minimizes the squared two-norm distance between a safe T and a T, so the correction changes the actor command as little as possible while enforcing constraints. The difficulty is AC power flow. The original AC equations are non-convex because voltage magnitudes and angles multiply each other. The slide uses SDP relaxation to obtain a convex safety problem. A complex voltage vector V is lifted into the Hermitian matrix W equal to VV Hermitian transpose. The rank 1 constraint would recover the exact voltage vector, but that rank condition is non-convex, so it is relaxed and replaced by the PSD constraint W positive semi-definite. Voltage bounds, power balance, and line capacity limits are then written in terms of entries of W. This gives a safety layer that is not a heuristic clipping rule. It is a physics-based convex projection that can protect the current dispatch step and reduce boundary trapping during exploration. The experiment uses a modified IEEE 14-bus system. The network diagram contains 14 buses, 5 thermal generating units, 1 wind farm, and 1 solar station. The red generator symbols show thermal units distributed at different electrical locations. The wind resource is connected near the upper right part of the network, and the solar station appears near bus 14. This placement matters because renewable variability does not affect only total energy balance, it also changes power flows through particular branches. A 14-bus system is small enough to diagnose and visualize, but it is complex enough to include transmission constraints, voltage constraints, generator limits, and ramping behavior. It therefore serves as a controlled testbed for the algorithm. If the method can lower operating cost while maintaining zero ramp, voltage, and line capacity violations in this system, the result supports the claim that physics-guided safe RL can behave as an operational dispatch tool rather than a reward hacking controller. The training comparison isolates the contribution of each component. Standard TD3 uses a conventional DNN actor and starts from random initialization. It learns slowly because it has no dispatch structure and no expert demonstrations. Guidance TD3 adds the expert experience buffer to a standard DNN actor. Its reward curve improves faster, showing that perfect dispatch samples help the policy move into better regions early. PINN-TD3 adds both the expert experience buffer and the PINN actor, but it does not include the safety layer. The reward plot shows 3 trajectories. Standard TD3 rises slowly and remains below the other 2 methods for much of training. Guidance TD3 improves faster, but its early trajectory still has instability. PINN-TD3 starts high and approaches the upper reward region quickly, Because the actor already carries physics and optimality information, the penalty plot tells the complementary story. Standard TD3 keeps a visible penalty tail, while the two guided methods drive penalties toward zero much faster. The inset at the final episodes shows that PINN TD3 and guidance TD3 stay close to zero, while the standard method still has residual violation. The lesson is that expert experience helps, and PINN structure helps even more. PINN TD3 can still violate constraints during training because it lacks the final projection safeguard. PGSRL adds the safety layer and therefore combines three advantages: a high-quality initial actor, expert experience, and strict single-step correction. The reward curve begins at a high level, falls temporarily as exploration exposes difficult regions, and then recovers to a stable high reward band. Around 12,000 episodes, the curve is already close to its long-run performance level. The three bullet conclusions are tied directly to the curve. High starting reward comes from the PINN actor and expert buffer, which prevent inefficient random exploration. Fast convergence appears because the policy does not spend most of training learning basic dispatch feasibility from scratch. High stability appears because expert gradient signals and safety-corrected interaction reduce destructive policy updates. For grid operation, this behavior is valuable. A method that only performs well after very long training is difficult to trust. PGSRL demonstrates that a policy can begin from a meaningful operating region, improve quickly, and remain stable as renewable and load conditions vary. The two plots measure whether the agent is becoming intrinsically safer or merely relying on the safety layer. The safety adjustment curve starts high, which means the actor initially proposes actions that require noticeable correction. The distance then drops rapidly and continues declining. After approximately 15,000 episodes, the adjustment distance stays near zero. This indicates that the actor has learned to generate actions close to the feasible set on its own. The penalty plot focuses on ramp constraint violations. The large spikes occur in the early stage where the agent is still learning how current dispatch choices affect future ramp limits. After several thousand episodes, the spikes become rare and small. The long tail near zero means the CMDP objective is doing its job. It trains the policy to internalize ramping constraints, not only to accept a one-step projection. Together, the two curves are stronger than a single reward curve. Reward can improve while hidden safety corrections remain large. These plots show that corrections shrink and ramp penalties vanish, so the final policy is both economical and operationally disciplined. The performance table compares four methods on operating cost and the three violation metrics. Standard TD3 has the highest cost, $39,000.0094 per day, and the non-zero violations in ramp rate, voltage, and the line capacity. The PINN method reduces cost, but still has voltage violation, because physics-informed approximation alone does not guarantee all operational limits. PINN TD3 achieves the lowest average operating cost, $35,000.4116 per day, with zero average violations in the tested scenarios. PGSRL has a slightly higher average cost, $36,000.0592 per day, but it also has zero average violations. The cost difference between PINN TD3 and the PGSRL should be interpreted as a safety premium. PINN TD3 is cheaper in these nominal test cases, but the text warns that under extreme load surges or drastic renewable fluctuations, it may still violate constraints. PGSRL trades a small amount of cost for a built-in safety mechanism that can enforce feasibility at the action level. In real dispatch, that trade-off is often acceptable because the cost of violating hard grid limits can exceed the small saving in operating cost. I close with one takeaway. Reinforcement learning for power system dispatch becomes much more credible when it is mathematically connected to economic dispatch, network physics, and hard safety correction. The method in this course is not only a neural policy, it is a structured decision framework. A PINN actor learns from KKT conditions. Expert experience supplies high-quality dispatch guidance. Twin critics separate reward from ramp risk. A CMDP controls multi-step ramp violations, and the safety layer projects unsafe actions into the feasible region. That combination explains why the experiments show high reward, fast convergence, and zero average constraint violations in the modified IEEE 14 bus system. Thank you.